In Lesson 3-2, we will discuss logarithmic functions. In Video 3.2.6, our learning target is for students to sketch and analyze graphs of logarithmic functions. In this video, we will discuss the properties of logarithmic functions. There are two types of logarithmic functions we need to discuss. Logarithmic growth functions, where the function is increasing from left to right, and logarithmic decay functions, where the function is decreasing from left to right. Now, for logarithmic growth functions, as we can see here, our graph is in quadrants 1 and 4, right? Quadrant 1 is in the upper right-hand corner. Bottom right-hand corner is quadrant 4. And our domain for a growth function is from 0 to infinity. So is our logarithmic decay function because, again, the graph is in quadrants 1 and 4. Our range is from negative infinity to infinity. Going back to the domain for a second, since our domain is from 0 to infinity, not including 0, we have a vertical asymptote at the y-axis for both graphs, which also means that we cannot use input of 0 or any negative value when evaluating a logarithmic function. Going back to logarithmic growth here, and for logarithmic decay, both functions have a y-intercept, never, because the y-axis is our vertical asymptote. Same with a logarithmic decay function. Both functions have an x-intercept at 1, 0. They cross the y-axis at 1. Our extrema, we don't have any. Extrema means like a maximum or a minimum. There is no turning point on this graph, therefore there are no extrema. Our asymptote, like we mentioned before, is the y-axis, or you can write the equation x equals 0 is the asymptote vertically. Our end behavior as x approaches 0 from the right side, that's what that little plus means. We're approaching 0 from the positive side of the x-axis. As we approach 0, right here, as we're getting closer and closer to 0, our y value is approaching negative infinity. Our end behavior is pointed down as we approach 0. And as we approach infinity, as x approaches infinity, or as we move to the right, our end behavior is pointed in the upward direction, so our end behavior is the limit as x approaches infinity is equal to infinity. Okay. Opposite is going on over here as we approach 0 from the positive side. So as we go towards 0 from the positive side of the x-axis or from the right, we would say that our end behavior is pointed up, so therefore our limit is infinity. And as x is approaching infinity, as we move all the way to the right on the x-axis, our arrow or end is pointed downward, therefore our limit is negative infinity. Both functions are continuous on the same interval. They have to say, we can't just say the function's continuous, because if the function's fully continuous, our domain would be negative infinity to infinity. But since the function is only continuous on a limited domain or restricted domain from 0 to infinity, we have to state that. So since both functions have a domain of 0 to infinity, when we state the continuity, we have to say it's continuous from 0 to infinity. One thing I did not mention yet is how we get these certain types of growth functions and decay functions. Up here, they've noted that f of x equals log base b of x is a growth function if your base is greater than 1. Very similar to exponential functions. When your base of your exponential function is greater than 1, it's an exponential growth function. And when your base is between 0 and 1, excuse me, between 0 and 1, greater than 0 but less than 1, on a logarithmic function and on an exponential function, you would have a decay function. Okay, so when b, your base, is between 0 and 1, For a logarithmic function, it is going to be a decay function. Same thing happens with an exponential function when your base is between 0 and 1. In example 6, we will be discussing graphing transformations of logarithmic functions. And we're going to use the graph of f of x equals log x to describe the transformation that results in p of x equals log of x plus 1, then sketch the graph of the function. Looking at this function, the original function f of x equals log x, I know that this is a growth function because our base is 10. This is a common log, so we know that f of x equals log base 10 of x. If I do not see this little base or subscript number, it is base 10. Now, another way to write that is f of x is equal to y, so I can write this function as y equals log base 10 of x. And this function then can be written exponentially, right? This log function, every log function can have an exponential form and a log form. Right now we're in log form, and we want to write this function exponentially, which would be 10 to the y equals x. So the exponential form of log base 10 of x is 10 to the y equals x. Now, if I graph this function, I'm just going to choose a couple of values. I know that my x value here, since my domain for every log function, or logarithmic decay and logarithmic growth, our domain is greater than 0. So I know my output for x here is going to be greater than 0. So what I'm going to do is I'm going to select, since y is our independent variable, I have control over y. Since x is by itself, x is dependent. And so what I'm going to do is I'm going to select values for y. Let's just say -2, -1, 0, 1, and 2. If I plug in -2 for y, that's 10 to the -2 power, which is 1 over 100. 10 to the -1 power is 1/10, or 1 over 10 to the first. 10 to the 0 power is just equal to 1. 10 to the first power is 10. 10 squared is 100. So what we have here is a table for the function log base 10 of x. And what we're going to do is sketch that graph. So I'm going to do my best to sketch the ordered pairs that I'm given. 1/100th is really hard to sketch here. 1/100th is going to be like 1/100th of the way to 1. And I'm down at -2, so we're very close to the y-axis there. 1/10 is a little bit closer to 1 than 1/100th, so I'm going to go out just slightly. And my y-coordinate is at -1. 1, 0 is my x-intercept. And then I'm going to go up to 10, +1. So way out here, we can see that our graph is going to have the general shape like this. Right? We know the logarithmic functions are in quadrants 1 and 4. That is, of course, until we start translating them. And if we start translating the functions, then we can shift outside of quadrants 1 and 4. So what we want to look at is what is happening when we start adding 1 to x. Notice my logarithm still has a base of 10, but now we're adding 1 to x. Now, what we've learned in the past with transformations of functions is that anytime a value is inside the grouping symbols and we're adding or subtracting inside of the grouping symbols, our function translates either left or right. Now, all horizontal translations take place opposite of the sign. So, if I see a +1, that means that the graph is going to shift to the left 1 unit. So what I can do on my graph is I can take all of these points and shift them 1 unit to the left. what I'm going to do is I'm going to go ahead and do that, sketch the graph of p of x on the next slide. So far, in this example, we've graphed the function f of x, which remember was 10 to the y equals x, or log of x equals y. Log base 10 of x equals y. Now what we want to do is graph the function p of x, which was the function f of x translated 1 unit to the left. So what we decided was that p of x, which was log of x plus 1, was really just a translation 1 unit to the left. So all I need to do is shift all of my x coordinates 1 unit to the left. Okay, so if I look at the table is going to look like this. If I shift the x coordinate here 1 unit to the left, I'm going to get 99. And my y coordinate is still 2. If I shift the x coordinate left 1 from 10, that gives me 9. So I'm at 9, 1. If I shift horizontally 1 unit to left and my x coordinate's 1, that means I'm going to be at 0, 0. If I shift 1 unit to the left, that's going to give me negative 9/10. And negative 1. And if I subtract 1 here to shift this x coordinate 1 to the left, that's going to be negative 99/100. And my y coordinate would be negative 2. So graphing this function, we'll graph it in green here. I'm going to shift everything to the left 1 unit. So I would be at negative 99/100, which would be in comma negative 2, which would be right here approximately. And I would be at negative 9/10, which is just slightly over from negative 99/100. And then I would be at 0, 0, right? This point has been shifted over 1 unit to the left. And this point here that I estimated at 10, 1 is going to be at 9, 1 now. Sorry. And my graph looks something like this. So the rate that the function is increasing isn't changing because our base is still 10. But all we've done is taken this graph and slid it over horizontally to the left 1 unit. In example 6, part B, we're asked to graph transformations of logarithmic functions. Part B says use the graph of f of x equals log of x to describe the transformation that results in m of x equals negative log x minus 2. Now what we want to do is we are going to use the graph of f of x to help us graph m of x. Now one thing I don't like about how they've written out m of x is that they didn't use any grouping symbols, so you don't know whether it's just log of x or log of x minus 2, and you should be subtracting 2 on the outside rather than on the inside of the grouping symbols, which we know will affect the graph. If the negative 2 is on the outside of the grouping symbols, then our transformation or translation is 2 down, versus a minus 2 on the inside is going to shift the graph 2 to the right. So we're going to go ahead and input parentheses around the x, and what we want to do is I'm going to go ahead and recreate the table we had for f of x, which is log of x. And we had negative 2, negative 1, 0, 1, and 2 as our y values. We chose the y values because remember 10 to the y is equal to x is another way to write the function log of x. And we had 1 100th, 1/10th, 1, 10, and 100 as our x coordinates. And what we want to do before we graph the function m of x, I want to describe what's going to happen to f of x in order to obtain m of x. So this minus 2 right here means a translation down 2 units. right? Anytime we subtract or add on the outside of the function, outside of the grouping symbols, that affects a shift up or down. So we're going to shift down 2 because it says minus 2. All vertical translations go with the sign. So a minus 2 means down 2. And a negative out in front here means a reflection over the x-axis. Right? Because we're changing our y-coordinates on our graph. If we had a negative sign inside, like if we had log of negative x minus 2, then that would represent, since the negative is in front of the x coordinate is going to switch sign, which would be a reflection over the y-axis. When you reflect points across the y-axis, the x-coordinate change. When you reflect points across the x-axis, the y-coordinates change sign. So what I need to do here is I need to come up with a graph of f of x, which we already had on the last page. And I'm going to use that graph to help me graph m of x. So here we had the function, let's just say this is what the graph of f of x looks like. Again, this is 10, 1, this is 1, 0, and we have 1/10, -1, and 1/100, -2. So this is a sketch of what the graph looks like. It's by no means exact. But what we want to do is take these points and we want to go ahead and graph m of x. So to start graphing this function, I'm going to start by taking all the points on f of x and reflecting them across the x-axis. So this point right here is going to be at +2 and 1/100th. So 1/100, 2. And this point right here is going to be at 1/10 still for an x-coordinate, but at +1 for the y-coordinate. This point right here will stay the same because any points that are on the x-axis and you're trying to reflect them over the x-axis, they stay on the reflection line. And right here, this point, if I reflected over the x-axis, we would be at 10, -1. So here's what my graph looks like if I've only done the reflection. I have not translated this graph yet down to. So to do that, I'm going to graph in red here. I'm going to go ahead and graph m of x because now I've done part of the transformation. I've reflected the points over the x-axis. And now I need to translate them down 2. So this point right here would be down, if I shift it down 2, would be on the x-axis. This point right here would be at -1. And this point right here would be at -2, right? The x-intercept, if you shift it down 2 units, the y-coordinate's -2. And if you shift this point down 2, you're going to have a y-coordinate of -3. So what the function actually looks like once you've reflected it and shifted it down 2, the graph m of x is right here in red. The table for m of x, if I make a table of values right here, if I make a quick table of values, when we reflected each point for f of x over the x-axis, what happened is all the x-coordinates stayed the same, but all our y-coordinates changed sign. So what you're thinking about here when we make this table is just with the reflection over the x-axis, what happens to all these y values is they change sign. So over here I would have a y coordinate of 2 and 1 and 0 and -1 and -2. But then what happens is that we shift the graph down 2 more units. So even though that this -2 actually becomes a +2 when we reflect over the x-axis, we then shift it down 2. So our first ordered pair would be at 100, 0. 1/100th, comma 0. Here at -1, that would become a +1, but then we shift it down 2 units and we end back up at -1. Here, this point actually stays the same at 1, comma 0. But then we shift it down 2, so our y coordinate should actually be 1, comma -2. Right? Our ordered pair, rather, should be 1, -2. Right? That's this point right here. And then the last point that we graphed, because we never graphed 100, comma 2, our last point should be an x-coordinate of 10. This, when we do the reflection, this 1 becomes -1, and then we shift it down 2 more units, which would put us at a y-coordinate of -3. So this would be our table for m of x. In example 6, part C, again we're using the same function f of x equals log base 10 of x to describe the transformation that results in n of x equals 5 times log base 10 of x minus 3. Now, when we're looking at the function n of x, this minus 3, since it's inside the grouping symbols, means translates 3 to the right. This multiplying by 5 out in front is a vertical expansion. Anything that happens outside of the grouping symbols, parentheses, etc., is a vertical transformation. Since we're multiplying by 5, and 5 is greater than 1, we would say it's an expansion. Now, what we're going to do to graph this function is, first of all, come up with a table for f of x, which we already have in the previous 2 examples. So I'm going to use those same values. This time I'm actually going to say -2, -1, 0, 1, and 2. We had -2 was 1/100th. -1 gave me 1/10th. 0 gave me 1. 1 gave me 10, and 2 gave me 100. Remember, the function log of x equals f of x really means 10 to the y power equals x. Now, what we're going to do is we're going to then translate all of these points 3 to the right. So translating something 3 to the right adds 3 to each of the x coordinates. Okay? So we're going to do this in phases. Okay? So to find n of x, right, we're going to start by shifting everything to the right. So if we shift to the right, that adds 3 to each of these x coordinates. So if I add 3 to each of those x coordinates, first of all, this would be 4, this would be 13, this would be 103. If I add 1/10 to 3, that's 3 and 1/10, and 3 and 1/10 would be 31/10. And if I add 3 to 1/100th, that's 3 and 1/100th. So that's going to give me 301 over 100. Take that back. Okay, so everything's fine. Just double checked my math here. 301 over 100 is 3 and 1/100th. 31/10 is 3 and 1/10. If I add 3 to 1, I get 4. 10 plus 3 is 13. 100 plus 3 is 101, or 103 rather. So what we're looking at here is our y-coordinates are going to stay the same. Shifting left or right does not affect our y-coordinates. It only affects our x-coordinates, which, since we're shifting 3 to the right, we were going to add 3 to x. Now, what we have to do is account for this vertical expansion by a factor of 5. So now what we're going to have happen is we take all of the values in this table after we've shifted all the points to the right 3, and a vertical expansion of 5 multiplies all your y-coordinates by a factor of 5. So now, instead of the x-coordinates changing, the y-coordinates are changing. So negative 2 is going to be negative 10 if I multiply it by 5. Negative 1 is going to be negative 5. 0 is still going to be 0. 1 is going to be 5. 2 is going to be 10. And the x-coordinates are unaffected by our vertical expansion. They stay the same, right? So 301 over 100, 31 tenths, 4, 13, and 103. So this is the table for the function n of x, where our graph has been translated 3 to the right and then expanded vertically by a factor of 5. I did this in phases. I started out with the table for f of x. I then shifted it 3 to the right. That's this table in the middle. And then the last table is expanding our function by a factor of 5 vertically. So these are the ordered pairs that I would graph, and I will do that on the next slide. On the last slide, we discussed coming up with the table for n of x equals 5 times log of x minus 3. We came up with this table here, and now we're asked to graph that function. I'm going to graph the ordered pairs, 3.01 and negative 10. I first got to label my y-axes here. We have 2, 4, 6, 8, 10. That'll be negative 10 there, and 2, 4, 6, 8, positive 10 here. And so I'm going to graph 3.01, negative 10. Just estimate where 3.01 is. 3.1 is just slightly to the right of that, and our y-coordinate is negative 5. And 4, 0 is our x-intercept. 13, 5 would be roughly here. Okay, because this is 4 right here. So I'm not going to graph 103, 10 because I have to go up quite a bit farther on the x-axis to reach 103. So all I really need to graph these log functions is like 3 or 4 points. I just need to see the bend or curve in it. And if I connect those dots, I have my graph of my function. Now, one thing you'll notice in this graph is it seems to cut off at like x equals 3. Well, that's because on a normal log function, the y-axis is our vertical asymptote. And when we shift this graph 3 to the right, our vertical asymptote actually shifts 3 to the right as well. So for this function right here, and I didn't sketch it super accurate, but our vertical asymptote would be at x equals 3. You can't, if you think about the domain of the function here, since you can't take log of 0 or log of any negative number, this expression here, x minus 3, has to be greater than 0. In order to do that, x has to be greater than 3. So at x equals 3, our function's undefined because that's where our vertical asymptote is. In example 6 guided practice, you're asked to use the graph of f of x equals ln of x, natural log of x, to describe the transformation that results in p of x equals natural log of x minus 2 plus 1. Then sketch the graph of the functions. You have 4 choices, A, B, C, and D. I would like you to work out this problem and then submit your answer.